Hi everyone. So it's my honor to be here to present our recent work. I'm Zhen. So the paper I would like to present today is the Centimani enable faster AI accelerator selection for the DNN training with the novel performance predictor. So this is also a collaborated work between the Binghamton University and the Argonne National Laboratory. So let's get started with some background. Okay, so as we can see, now the machine learning is everywhere, and it has become more and more popular with the applications ranging from the objective identification and the car brand detection to the human pose estimation and some scientific discovery using the machine learning techniques. So it also has felt some significant impact in the generated AI, such like some real-world examples, such like the AlphaGo, ChatGPT, DANI demonstrate the broader influence and the potentials of the machine learning techniques. Okay, but as the field of the machine learning evolved, the deep learning models are becoming increasingly complex and harder to train. So the complexity is reflected in the growing size of the trainable data size and the number of the trainable parameters. So as we can see from the right figures, the right two figures, so we can see the numbers of the training data set size and the trainable parameters is going up. At the same time, the computational power required for training the model on the right side, which as we can see in the figure measured in the floops, is growing significantly as well. So the three figures provide us some insight into the trees, which can highlight the elasticity the demands for the DNN training. Okay, so to meet the diverse and the demanding computational requirements for the DNN models, a variety of the hardware has been proposed, such like the traditional CPU from the Intel, AMD, ARM, as well as the GPU from the NVIDIA, AMD, and the Intel. Additionally, specialized AI accelerators on the right side, you can see, are also designed and proposed to handle some specific DNN tasks. So I will introduce more details about the AI accelerators in the following slides. Okay, so the workload, including the DNN applications workloads, such like the CNN, RNN, GAN, GNN, transformers, reaching transformers, and some other models are tried to run on the such like the kind of the hardwares. Okay, so now we can see some problems. So we can see in the first challenge in the field is the mismatch between the hardware capabilities and the requirements of the different machine learning workloads. So we can see the counter machine learning workloads are highly heterogeneous. So it involves diverse input, diverse computational need requirements, and some different memory access patterns. And this heterogeneity leads to the efficiency if you randomly select the one hardware to train your model from a lot of the options. Such we can see on the right side, we can see we have a lot of the traditional CPU, GPU to train our model. We also have some new hardware to train our model. If you just randomly to select one from them, there will be need to a lot of the mismatch and the efficiency from them. Okay, so resulting a suboptimal performance and low utilization, hardware utilization. So we are trying to address that. Okay, so if we try to make a deep understanding with this scenario and this part, so we are trying to train a very common ResNet 50 model with the half precision on 5 platforms, such like the one NVIDIA GPU, which is the A100, and the 4 new proposed AI accelerators, such like the Supernova SN30, GraphCore, Bow IPU, Cerebras, CS2, and the Habana Gaudi 2. This is also from the Intel. Okay, so as you can see from this figure, the x-axis is the name of the AI accelerators, and the right and the the y-axis on the left side is the training throughput. So we can see a lot of the different numbers for the training throughput. For example, so the Habana Gaudi 2 outperforms the NVIDIA A100 GPUs with 2.70 times higher throughput. However, if we try to move to the y-axis on the right side, we can see the hardware utilization is not a reliable cost platform indicator of the performance. As well, we can see the graph core IPU, which has a very similar peak performance with the NVIDIA A100 GPU, but it can achieve around 1.5 times speedups over it. So as we can see in these figures, the hardware utilization is not a good indicator for us to get the estimation from it. Okay, so the next one is another challenge is the different AI accelerators requires distinct hyperparameters to achieve the optimal training throughput. So, for example, the batch size is a very important hyperparameters for training a DNN model, and such like I can take something as examples in these figures. The graph core Bo IPU needs 64 times larger batch sizes than that's used in the Sapalova SN30. Okay, you can see in these figures, the batch size used in Sapalova is 32, and the batch size used in graph core is 1024. Okay, even when we was using the same experimental setting, so the variability complicates the process of tuning a model for the different hardware platforms. Okay, now we try to think about if we can reuse some traditional ideas or the previous work to address the challenges. Such like the first one is we can use some DNN benchmarks to help us to predict the performance, such like we can use the ML proof, Zhou bench, such like kind of the benchmarks to predict the performance. But however, this approach are not accurate. So because the benchmarks often cover only limited number of the DNN models, and the second one, if we the second approach is to implement your model on real hardware. But in this approach, it requires extensive human effort to implement the models on different hardware, and it will take a lot of time to select the one with the best performance among them. Okay, and the last approach is to make a prediction based on the hardware utilization. But in our previous slides, we can see the hardware utilization does not generalize well across the different AI accelerators. So based on the considerations, we advocate for a hybrid approach that combines the experimental and analytical method to make the performance prediction. Okay, so to begin with our research, we are trying to analyze and compile the different AI accelerators and try to get some insight from and get some observations from them. Okay, so the AI accelerators are designed to enhance the performance by achieving high parallelism, fast memory transaction, and scalability. So I list the 4 AI accelerators, and I list some of the hardware details in this slide. And for instance, the Sapalova SN30 deploy the pattern computing unit and the memory unit to reduce the memory movement inside the chip. And while the Cerebras CS2 leverage the Collins tensor core and the intensive on-chip memory to improve the performance and also improve the parallelization. And the graph core Bo IPU also utilize the BARC synchronized parallel model to achieve the high parallelization, and the Habana Gaudi 2 feature a heterogeneous architecture, which include a couple of the tensor processing core and one matrix math engine to get a better performance. So we can see they have a different hardware design, and also they have to deploy some different software to use this kind of hardware. Okay, we're trying to analyze this kind of hardware, and we'll try to get some observations for our performance modeling. Okay, so in the next slide, we can see we are trying to get some observations based on the last slide. So we can see some significant difference in the hardware and the software implementations for across different AI accelerators. And also they can share some commonality in memory subsystems and the data management. Such we can see in these figures, they still use some traditional computing units and some memory units and they use some bus or they use some link to connect the different units together for the communication. Okay, so the second observation is predicting the execution time of the entire DNN training on AI accelerators is very difficult and almost impossible because the hardware utilization offers limited assistance in this regard, such like if we use some traditional hardware simulators, such like the GM5 or some other Model Sim or some other hardware simulators, it will be very slow, and sometimes the AI accelerators didn't release all of the hardware details to us. So it's very hard to simulate the hardware using some simulators. Okay, so the last observation is choosing the appropriate batch sizes requires the considerations of hardware limits and the software optimization. Okay, so next I will introduce our solution. So our solution the name of our solution is the Centimani. So the meaning of this name is the man with more than 100 arms. So we hope it can handle all kinds of the different hardware design, software design, and it can also handle all kinds of the AI accelerators effectively and efficiently. Okay, so Centimani is designed to address those challenges by making direct performance prediction for the DNN training on various AI accelerators. So it will select the optimal hyperparameters in the software abstraction and deploy decoupled performance models in the hardware abstraction. Okay, so to predict the execution time for the different training phases separately. So after that, we can select the one with the best performance among them. Okay, we also use the execution modeling to connect the software abstraction and the hardware abstraction, and it can help us to connect two of them. Okay, so one critical part of the Centimani is to select the right hyperparameters. So we will try to use the batch size as examples to say how can we select the batch sizes among the different candidates or different options. Okay, so if we use the default, so we can think about if we just use the default setting, such like if we just use the default hyperparameters used on GPU, so what will happen? So we can see if we try to use the default batch sizes from the GPU, like the NVIDIA A100 to the AI accelerators, so we will have a lot of the out-of-memory problems or errors. So however, if we try to use the optimal ones, we can get the significant speed up as at least in this table. So we can get some speed up in this table. Okay, to address that, the Centimani memory mode will classify the different tensors into 5 types. And we can see on the right side, and we try to estimate the memory consumption for the different types at the different level to get the fine-grained estimation. Okay, so then how can we use the memory model? So we're trying to build a memory estimation model, and it involved 2 steps. So the first step is to traverse the computational graph of the DNN models to predict that fine-grained memory consumption. And the second step, we will try to calculate the memory usage of each level of the memory, such like the on-chip memory and the off-chip memory. So next, we will try to, we already have all of the things to get the memory. So we will try to use the memory estimate model to select the optimal batch sizes. We will try to maximize the parallelism where we were staying within the hardware constraints based on the attached formula. So we can see in this formula, we'll try to get the best parallelization, and we are trying to make all of the used hardware is still in our hardware limits. So the care of memory management is essential for achieving the high training throughput on the device accelerators. Okay, so to make the accurate predictions, Centimani also uses the decoupled performance models that separately estimate the execution time for the data loading, pre-processing, computation, and the communication stages. And by deploying the different prediction models to each training stage, so we can get a more accurate prediction. And for each model, so there are more explanations of paper. So we will try to, if you want to know more details for each stage, you can just read our paper to see. We have a lot of formula to explain how can we get the more accurate execution time for the different stages. And the Centimani performance model also considered the two overlaps between the different training stages. For example, the data loading and the pre-processing can overlap with the computation, and the computation can overlap with the communication in distributed training scenarios. So these overlapping mechanisms can help us to accurately predict the total training time by considering the concurrent execution of the multiple stages. Okay, for the evaluations, we use the 4 AI accelerators. The first one is the Supernova, second one is the Graph Core, third one is the Cerebras, and the last one is Habana. So we test the multiple DNN models and the data set as we list in this table. And then we also compare the Centimani performance against other baselines, such like the roofline model, the hardware utilization-based model, and the similarity-based model. Okay, so in these figures, we will see some accuracy of our results. So this figure shows the prediction accuracy of the Centimani for the single device training across the 4 different AI accelerators. And the x-axis is the model name, and the y-axis is the prediction accuracy. So as we can see, the Centimani achieves an average prediction accuracy of the 93.1% for the single device training, and significantly outperforms some other baselines. Okay, and we can see some highlights, such like it can outperform similarity-based benchmarking on the UNet, Candle, DNN, and the OpenAI GPT-2. And we can see it performs much better than the prediction similarity-based model and the hardware utilization-based model in the Graph Core Bow IPU, just because it's a specific hardware design. Okay, we present the throughput prediction and for the various different models in this figure, and also we present the price performance ratios normalized to the NVIDIA A100 GPU. So as a result, we can see the Habana Gaudi 2 achieves the best throughput on the Resonant 50 model due to its peak performance and the matrix multiplication engine. And meanwhile, the Graph Core IPU offer an excellent performance price ratio due to its low rental cost and high training throughput. Okay, so this slide shows some decoupled models construct for the 4 AI accelerators, including some micro benchmarks for the operators, such like the batch normalization, the linear transformation, and the max pooling 2D, and the operators are tested in both single and half position. Okay, and the figure on the lower side, lower position is the multi-device training. And as we can see, on average, we can get the 90.4% of the prediction accuracy for training the model on multiple devices. And also we study the overhead of the Centimani, and the major overhead include some measure the memory capacity, memory bandwidth, transmission bandwidth, and also some communication bandwidth between different devices. And also we need to construct the micro benchmarks and the roofline models for each accelerators. And we need to collect some memory consumption from the mass library. And we need to traverse the computation graph to make the memory consumption and the prediction performance prediction. So we just need to, for the first three components of this overhead occur only once for each AI accelerator, and the fourth component occur once for each DNN model. So overall, the overhead of Centimani is significantly low than the overhead of the porting or implementing the DNN models to new AI accelerators. Okay, to make a conclusion, so we introduce Centimani is a novel performance predictor that accesses deep learning researchers or participants in selecting AI accelerators for training the DNN model with higher throughput or lower cost. And the primary idea behind the Centimani is to combine the experimental and the analytical approaches to predict the execution time for the DNN model on each AI accelerators. And we evaluate the Centimani with a 6 typical DNN model on 4 AI accelerators and find it makes execution time prediction with the average accuracy of the 93.1 and 90.4% for the single device and the multiple device training. Okay, thanks so much. I'm welcome to any questions.